All right, so I want to talk about bringing AI out into the world, which is a source of pride and joy, the best of times and the worst of times. Radha's introduction is going to set me up really well for this talk. For me, the thing that you're going to see is I love building systems, going from robots that get wet to robots that preferably do not. And then really building on a trend recently focusing on autonomous cars. So let's talk about the worst of times in autonomous cars and where we are, maybe some incredulity. There's a lot of hype about autonomous cars. And so everyone, you can read a news report basically every day about someone's going to solve the autonomous driving problem once and for all, and they're going to be out, and it's going to be great. And you might be thinking, didn't I read the same press release 2 years ago? And yeah, you did. So maybe, can we measure the progress that we're making for autonomous cars? Let's quantify how we're doing. So here we got a scale that we're going to put some data on. This is miles per disengagement. Think about this as how far can the car go between something bad happening. And this is on a log scale. And this, of course, is year. So let's go out to the real world and find some data. All right, so first of all, how good do autonomous cars need to be? So let's suppose that they need to match human performance. There's actually really good arguments that that's not the right number. But let's run with that. How well do humans drive? How many miles does a human drive between fatalities? Not a rhetorical question. 10 million, I heard. 1,000? Other numbers? 100,000. I know some people know the answer to this. About 100 million miles, right? People drive an awful long way between killing people. And so the reason we have 40,000 people dying every year on roadways, it's actually not because people are really bad drivers. It's because we do so much driving. And this is really why autonomous driving is so hard. It's not that we have to build a vehicle that works pretty well. It's that we have to build a vehicle that works with that many nines. How many nines is that? Like 8 nines or something like that. Really hard problem. All right, so let's see how we're actually doing. We can go back in time. Oh, that's here, 10 to the 8th, right here. So that's the bar that we want to reach. Here's zoom back in time to 2004, the Desert Grand Challenge, which did not go well. Anybody recognize that car? Yeah, CMU, that was the winner. So they made it 7 miles down the path. So kind of a rough start for autonomous driving, but it does give us a data point. They went about 10 miles in 2004. There's our data point. All right, let's fast forward a little bit. In California, every autonomous vehicle company that operates on California roads has to publicly disclose their disengagement rate. So we can go and collect some data. Here's Waymo. They report the highest number. We can argue about whether we believe that number or not. But they claim currently 10,000 miles between disengagements. All right, that's easy. So 10 to the 4th, go over here, 2019. Great. So now let's be optimists. Let's assume that there's a Moore's law kind of improvement rate, that technology is going to grow faster and faster at sort of an exponential rate. How long will it take for us to get to the blue dashed line? And those of you who are really good at math on the fly, 16 years. So 16 years from today, assuming that we continue to double performance every 16 months for us to match human performance. And again, assuming year over year exponential improvement in the technology. So I think we live in the worst of times. That's a long way to go. All right. That's not a feature. There we go. So let's pop up a little bit. What is it about autonomous driving that's hard? Well, perception's hard, regulatory environment is hard. There's a lot of things that are hard. But for me, I really think that the hardest thing about building an autonomous vehicle is the high-level decision-making. So think about this as the interactions between you and all of the other agents in the roadway. So here's a very simple case. You're a car. There's a pedestrian. Looks like they're going to cross the road in front of you. Now, maybe the textbook thing to do is to wait for the pedestrian. But if you brake for every pedestrian that's standing on the side of the road, that's going to have a bad outcome. You're going to get rear-ended. People are going to get annoyed with you, and so forth. So one of the real challenges is for you to figure out, hey, what's that pedestrian actually want to do? Do they want me to slow down so they can cross in front of me? Or do they want me to speed up so they can cross behind me? That's an example of a really simple high-level decision. You've got other high-level decisions of, I'm behind a slow-moving car. Should I pass them? Should I take the next exit? Should I take the freeway or should I take the side roads? All of those sorts of high-level decisions are really where a ton of the hard problems live. Now the question is, why is that hard? And it really comes down to the real world is hugely multidimensional, right? So you imagine that pedestrian crossing scenario and all of the factors that would change the answer, right? So what if it turns out that there's fast-moving traffic on the other side? Is that pedestrian going to cross when there's traffic whizzing by in the other direction at 50 miles an hour? No. It actually makes your decision to go faster more likely, right? You should probably just go. What happens if there is a bicyclist that's blocking their way, or a double parked car, right? So the challenge here is not this simple situation where you've got this one interaction between here. It's actually complicated because you can have 15 other agents all interacting, creating a really high dimensionality input space. And so now the problem that the autonomous car has to make is, for every situation that the car might encounter, make the right choice. And that's where we end up in this terrible loop of collecting edge cases. So how many of you have heard of edge cases, and we need to drive millions or maybe billions of miles to make autonomous cars work? Here's what's going on. You got a pile of engineers, really smart. They write down a bunch of rules about when the vehicle should do something. Then they put the car out into the world, and they drive it around for a while until the car does something dumb. Then the engineers go and they write up a new scenario. It's a new input configuration that they want to test for their vehicle. And now the engineers scratch their head and try to figure out how to make the car behave differently in this one situation that's different from all the rest. And then they go back around and around and around. So millions of testing miles later, you're collecting these edge cases one at a time. Every new data point that you get in this high-dimensional space is making it harder and harder for you to actually build a system that has any hope of generalizing. All right, so I want to tell you a little bit about how we're approaching this problem. So really, the first part of this talk is about how do we manage complexity in autonomous vehicles so that we can try to escape this cycle of collecting millions or billions of miles and lots of edge cases. And so the algorithmic tool that we've brought to the party is called multi-policy decision-making. And the basic idea is pretty simple. We're going to give the vehicle a bunch of think of them as almost idiot savant controllers. Right? One of these is a policy for the vehicle that's really good at following the vehicle in front of it. Another policy is one that's really good at doing the same thing but is aggressive about it. And another one is conservative. Another one is good at making passing maneuvers. And now the question is, how do we decide between which of the things we should do? Right? I just refactored the problem so far. But how do we decide which of the things we're going to do? Well, instead of writing down a bunch of rules in advance, what we do is we build a simulator. This is not the simulator that runs on AWS. This is a simulator that runs on the car. We're building a mirror copy of the world around us, and we try all of those policies in the simulator. And the simulator takes into account the closed-loop dynamics of that pedestrian with the bicyclist, with the oncoming cars. And we just try all of the different things in our system in the simulator, do this a bunch of times, each time sampling from our prior about what other people's intentions and state are, and then we vote. And then we essentially elect one of these policies becomes the policy for the vehicle. And so what the exciting thing about this is that it helps us in a lot of ways. The development time goes way down. I can go out and ask an engineer to build a new policy, and we can dump it in the system, and then the simulator essentially elects which policy I should run at the right time. And I don't have to go back and rewrite all of my rules. That's a huge advantage. Critically, we don't have to prescriptively say, in this situation, do X, and in this situation, do Y. We say, here's a bunch of stuff you could do. Figure it out. And that eliminates a huge amount of engineering time, allows us to build these systems in a way that we can actually put in the world. All right. So here's a really simple example from the world of indoor robots. Here's a robot with 3 really dumb policies. So it's got the ability to stop. It's got the ability to treat the world as a bunch of static obstacles and just do sort of a minimum length path planning around it. And it's also got the ability to pick an agent in the world and follow them. Are they going the direction I want to go? I don't know. But it's a thing I could do. And so I can try all of these things in the simulator, keep switching back and forth between these different strategies to try to find a set of behaviors that actually get the robot to behave reasonably intelligently. And so here you're seeing, if it plays, nope. Technology. There we go. So we have some prior estimate of the world. We keep initializing these very simple sort of cartoon diagram simulations of how the agents are likely to interact with each other, trying different strategies for the ego agent. We score them all, and then we finally pick something to do. So here's the kind of behavior that you get. The robot's driving around. It gets stuck. It doesn't see a path, so the stop policy looks like the best policy. A little while later, a path opens up, and it says, OK, great. I'll just treat these guys as static obstacles and go around. Here's another case where they've got two people blocking our path. We're deciding, well, should I follow this guy? No, that guy's no good. How about let's follow this guy? And this is really cool. We're getting really emergent behavior from the system from 3 really dumb policies. And when you interact with this robot, it feels different than most of the other robots that I've built in the past. Here's another example where we're out in that is amazing. I didn't even know I could do that. Here's another example where we've got the robot operating in the open. In this case, operating at quite high speeds with other human agents operating around. And in this case, the policies that it's choosing are which angle should I go, which speed should I go, and it's constantly modulating between these. The individual policies are trivial to write, but the simulator makes them look smart. And that's kind of a cool thing. I'll skip this slide, but it's cool. This symposium is about AI in society. Let's talk about AI in society. The thing that really motivates me is solving real-world problems. And one of the real-world problems that is really hard is congestion. So this article ran in the LA Times recently pointing out that the average speed of a taxi in Manhattan is 4.7 miles an hour. But don't worry, New York has a plan. Anybody know what their plan is? Darn it! Ben's very smart. The plan is congestion pricing, which is the idea that we're just going to start charging people to go downtown. Who does that serve? Who is that good for? Rich people. Right? And that's a huge problem, not just because bleeding heart liberal or whatever else, but people who work need to get to their places of employment. It drives commerce. And so if you are building a transportation system that denies the ability to move around to all but rich people who can drive around in their robo-taxis, being entertained as they clog up the roads, that is a huge problem for not just equity and access and transportation, but for the functioning of the economy. And so we're really excited about helping to create systems that make the world more walkable, more livable, more equitable and access, and reverse this vicious cycle of public transportation sucks, so nobody rides it, so there's no funding for transportation, so it gets worse. So how can we build systems that reverse that by creating transportation systems that are so good that even the rich people will ride it? And the solution to that is autonomous vehicles, because autonomous vehicles can fundamentally change the level of service and experience that riders have. Instead of waiting for a bus that comes by every 20 minutes, you can wait for a vehicle that will be by in about 3 minutes. And that's more of the Lyft or Uber kind of experience that people want. So we're really excited about that. This is what May Mobility is doing. We just hit 100,000 rides on public roads and mixed traffic. We're live we've launched in Detroit, Columbus, Providence, and Grand Rapids. So thank you very much. I think we have 1 or 2 minutes for questions, because I was a bit of a windbag.
If the simulator is so good, why not just use the simulator all the time to make decisions?
Yeah, so the question is, if the simulator is so good, why do we need these policies in the first place? Why don't we just pick the right thing to do? It's about limiting the dimensionality of the search. So think of this as a partially observable Markov decision process. We're basically saying, hey, instead of finding the best policy amongst all policies, find the best of these 6 policies. And that's something that we can evaluate fast enough to do in real time. Yes? Yes, so basically the question is about, I'll paraphrase, what are the rates of accidents and other types of events as opposed to fatalities? Injuries are about an order of magnitude less, so about 10 million miles between injuries, and collisions of some kind are about another order of magnitude less than that. So exactly whether disengagement equals an injury or fatality, we can argue about. But the reality is that 16 years is that the time is still a long way away.
Hi,
Great
Ed.
question.
So here.
I have no idea. OK, great. Hey.
So wanted to know if the simulator, if there is an error between what the simulator is predicting as the other models and the real world.
Yeah.
How does your model take into account of that error?
Yeah, there's this pesky thing, free will. The simulator's trying to make predictions 15 seconds ahead. All of our predictions are wrong. But we sample from our prior and run each policy in each scenario thousands of times. And so while any individual prediction is surely wrong, we do get this sort of interesting spread that if I run policy A, I get these kinds of outcomes. And if I run policy B, I get these kinds of outcomes. So I can choose between policy A and B based not on any specific prediction, but based on sort of the constellation of outcomes. And I think I'm out of time, but happy to talk afterwards. Thank you.
Let's give Edwin a round of applause.